For each of the following functions, describe or determine the domain and range. Now we're going to give it or describe it in interval notation and set builder notation. Okay, now this first one is a quadratic function. Okay, so it's going to look something like this because it's actually in vertex form. It is shifted to the right 4 and up 5. And as I said, it's a parabola opening up. So its domain is all real numbers. You can evaluate it at any value of x. But its range, the outputs, well, if you look at the graph, the outputs are always greater than or equal to 5. It is always at 5 or above. So putting that in interval notation, and we'll throw set builder notation over here. Interval notation, all real numbers would be negative infinity to infinity. We are not including either of the ends there because they are, well, infinity, they're directions. We can go towards infinity, but we don't actually get to infinity. So that would be the interval notation there. Well, in set builder notation, it's a whole lot better. We have x such that x is a real number. All right? They both represent the same thing. They're just written two different ways. Now, often interval notation is used. In fact, it's used a little more frequently. But set builder notation it's very descriptive. It shows you exactly what's there. So they're both valuable. Now, interval notation for greater than or equal to 5 would be a left endpoint of 5 going on to infinity. And we are including 5 because we have a greater than or equal to. Set builder notation would be y such that y is greater than or equal to 5. Okay. Part B of this. The domain for this function would be anything that we can plug in that does not make us have a negative square root. Okay, we want real values here. So we want, in the end, for our domain to be the numbers such that 3x plus 2 is greater than or equal to 0. We can take the square root of 0, just not a negative number, and get a real value. So that would mean if we subtract 2 divided by 3, x is greater than negative 2/3. So in interval notation, we would write that as negative 2/3 going on to infinity, including negative 2/3. And in our set builder notation, so again, I'm writing the same description twice in two different forms. X such that x is greater than or equal to negative 2/3. Now our range will be a little bit trickier because you can plug in anything greater than or equal to negative 2/3, but what outputs do you get? Well, if you evaluate that at negative 2/3, you actually get negative 1. So our outputs are greater than or equal to negative 1. In this case, our graph looks like this. We have our lowest point here. This lowest point is at negative 1 is the y value, and negative 2/3. So the domain is going to the right of negative 2/3, greater than or equal to, and the range is greater than or above negative 1. So this would be y, such that y is greater than or equal to negative 1. Okay. This next function we have is a rational function. The problem we have here is that we cannot divide by 0. Well, what number could you put in there that would make that 0? Well, 2. So x cannot be equal to 2. That's my scratch work. So my domain over here is, well, my interval notation for this would be negative infinity to 2. And if you notice, we are not including 2. We have We're not including 2 in either of those intervals, so it's actually excluding 2. That's the way to write that. In interval notation, we have x such that x is not equal to 2. All right. Our range, this function actually has a horizontal asymptote of 0. This function is never actually 0. The graph looks something like this. We have at the value of 2, an asymptote, and it does this. So our y value is not 0. So we'll write that as negative infinity to 0, union 0 to infinity. And in set builder notation, y such that y is not equal to 0.